Hello, I'm Greg Miller, and I'm going to update you on new tools for metrological traceability. I'm going to speak about harmonization protocols for establishing metrological traceability, and then address correction for non-commutability of a matrix-based certified reference material. ISO published an updated version of its 17511 document on metrological traceability. The updated version includes metrological traceability based on a harmonization protocol. The harmonization protocol replaces these inadequate calibration hierarchies described in 17511. At the top you see traceability to a non-commutable matrix-based reference material. Of course, reference materials are intended to be commutable, but they are not commutable in practice for all applications. At the bottom, you see traceability to a manufacturer's working calibrator, which applies to situations when there is no other higher order reference material available. So a harmonization protocol provides metrological traceability to an international harmonization protocol for a calibration hierarchy, shown in the upper right hand of the diagram. This protocol specifies harmonization reference materials, which are usually a panel of clinical samples, which then fulfill the position of a secondary matrix-based reference material in a calibration hierarchy. ISO published a new standard last year along with revised 17511. The new standard 21151 specifies requirements for international harmonization protocols establishing metrological traceability of values assigned to calibrators and to human samples. A harmonization protocol is suitable for use when there is no fit-for-purpose certified reference material or reference measurement procedure. And this new ISO standard will enable JCTLM to list harmonization protocols in its database. The first requirement in a harmonization protocol is to qualify measurement procedures for inclusion. First step in that is to ensure measurement procedures measure the same quantity or the same molecular form of the measurand. Meaning they have suitable selectivity for the measurand. The second key component is that measurement procedures have adequate performance. Their precision or repeatability is acceptable, and the response is proportional to concentration over the measuring interval. The next step in the protocol is to specify reference materials, which, as I already mentioned, are usually a panel of clinical samples. The protocol needs to specify how those samples are collected, what patient characteristics are needed to obtain the necessary samples, how they're stored, pooled if pooling is involved, any supplementation that may be involved, commutability assessment if required. And the second key step is a process for value assignment of the clinical samples, which in most cases will be some form of a trimmed all-method mean statistical approach. The next step in the protocol is to describe how to derive the measurement procedure-specific correction that will be applied by each manufacturer. The clinical samples used as harmonization reference materials are measured by all the medical laboratory measurement procedures involved in the protocol, and those initial results are used by each IVD manufacturer to develop a measurement procedure-specific correction algorithm to achieve equivalent results for clinical samples. And then the manufacturer will apply the correction algorithm in their calibration hierarchies. The next requirement is to apply the measurement procedure-specific correction and confirm that it does in fact produce equivalent results for clinical samples for the harmonization reference materials. And then the next step is to validate the harmonization protocol. using a reserve set of clinical samples for this purpose. The reserve set is usually prepared at the same time as the set used for harmonization reference materials and held in reserve under stable storage conditions to be used for the validation step in the protocol. Again, the end user medical laboratory procedures applying their method-specific correction algorithms will produce a set of results for this reserve set, and if they are equivalent, that validates and confirms the success of the harmonization protocol. The next requirement in the protocol is to specify surveillance over time to ensure the results remain harmonized. The most common use for this purpose is an EQA system or proficiency testing system using commutable samples, or other schemes, for example, based on patient median assessment, can be used among all the medical laboratory measurement procedures to confirm they continue to produce equivalent results for clinical samples. This provides feedback both to the laboratory and to the IVD manufacturers on the successful continuation of harmonization, and will identify if repeat harmonization protocol is needed, for example, based on a reserve set or preparing a new set of harmonization reference materials. And also is a provision to provide harmonization for new or improved measurement procedures that come on the marketplace after the time the initial harmonization was achieved. Now let's turn our attention to commutability of certified reference materials. Commutability is a property of a reference material such that the same amount of measurand in the reference material and in patient samples produces the same measurement results among different measurement procedures. Or stated a little bit closer to the VIM definition, commutability means acceptable closeness of agreement between the results for the reference material and the patient's samples for all combinations of measurement procedures. Diagrammatically, a commutable reference material is shown in green here and has the same relationship between two measurement procedures that is observed for a set of clinical samples. When a certified reference material is used as a calibrator and is commutable for use with these two measurement procedures shown in this example, the two measurement procedures then produce the same results for clinical samples. A non-commutable reference material has a different relationship between two measurement procedures than observed for a panel of clinical samples. When a non-commutable reference material is used as a calibrator, the calibration attempts to achieve equivalent results between the two measurement procedures, but in fact, because of the non-commutability bias, the patient results will in fact be different between the two procedures, and this non-commutability bias causes the clinical samples not to agree among a group of measurement procedures. So this is the classical ISO 17511 metrological traceability diagram, and just points out that a non-commutable matrix-based calibrator breaks the traceability chain at the position of the secondary commutable reference material. In addition, also in the ISO standard is a certified reference material, secondary commutable reference material, may be the highest order available material, and again, if it is not commutable with clinical samples for all of the measurement procedures for which it is intended to be used, again, the calibration hierarchy is broken at that position. So here's an example with numbers. A commutable matrix-based secondary certified reference material is used to calibrate the manufacturer's selected measurement procedure and subsequent steps in the metrological traceability chain. If the CRM has a value of 77.2, the working calibrator might have a value of 81.4, the end user calibrator some other value based on the calibration hierarchy, producing a result of 64.3 for a clinical sample. These are just example numbers But if we look at what happens if you have a non-commutable secondary-based reference material for a particular manufacturer's measurement procedure, and in this case I've shown an example with 15% non-commutability bias. So instead of the working calibrator having the correct 81.4 value, it ends up with a 15% higher value, 93.6. And that non-commutability bias gets propagated through the rest of the calibration hierarchy to produce an incorrectly biased sample, a biased result for the clinical sample. Now, non-commutability bias of a certified reference material can be corrected, and this work was published, as you can see at the bottom, by the IFCC Working Group on Commutability and Metrological Traceability last year. And this diagram shows how the correction process works. So in the calibration hierarchy, a method measurement procedure specific correction, in this example it will be a 15% correction, is applied. And so the value assigned to the working calibrator now becomes corrected for that 15% non-commutability bias. And so it has a value in the green column where it says value with correction for 15% non-commutability bias. And now we propagate through the rest of the calibration hierarchy to produce a correct value for the clinical sample result. So in this manner, if a certified reference material is commutable with patient samples for use with most measurement procedures, but there are some for which it turns out to be non-commutable, then this correction step can in fact produce metrological traceability to that certified reference material by introducing a correction. Now, the correction does add uncertainty, and the supplemental material that accompanies this paper has a detailed worked example in an Excel spreadsheet on how to do a experimental design to minimize the uncertainty added into the calibration hierarchy. Now, the correction requires the non-commutability bias to be stable within acceptable limits over time. Meaning, is the difference in bias that was observed at the preparation of the material the same as it is today, some number of years later when that material has been stored? And key stability considerations include the stability of the measurand, the stability of the matrix, and the stability of the measurement procedures that are going to be applying a correction. And highlights are the reagent lot or the formulation changes, calibrator lot or formulation changes, and any changes in instrument performance due to replacement parts, maintenance, etc. over time. So the path forward is we have more tools in 2021 that can address metrological traceability in some of the more challenging situations that have been identified over the past number of years. And it's always important to remember that we need to work as a team, the laboratory practitioners, the IVD industry, and the regulatory agencies to achieve standardized results for the betterment of patient care. Thank you very much.